Hello, this is Teach Nichols, and this video is on solving multi-resistor circuits. The essential question is, how do you use both conceptual reasoning and also mathematics to solve complex circuits? Let's start with the sort of circuit laws. These are the big ones you're definitely going to want to remember, and you can cite them by name if you're trying to justify an answer. The first one is known as Kirchhoff's junction law for current, and this law is a formulation of the conservation of mass principle. It basically says that if there's ever a junction of wires, so a place where two or more wires come together, then the current into that junction has to equal the current out. You're not allowed to lose any electrons from a junction. The second big circuit law is called Kirchhoff's loop law for voltage. This comes from conservation of energy, and it says that in any single connected loop of wire, the delta V across the entire loop is always going to be 0. In other words, by the time the electrons make it back to their starting spot, they should have exactly the same energy they had the last time they were there, right? It's kind of a self-sustaining situation. You might gain some energy passing through a battery at one point in that circle and then lose it in resistors, but by the time you get back to where you started, your overall energy has stayed the same. Ultimately, you can solve circuits using simultaneous equations that come from these laws, which is sort of a slow but easier to follow process, one that tends to work in more complicated cases, or by using a combination of logic and proportional reasoning with a few equations, which tends to be a lot faster. So really good for like multiple choice kind of questions. The first thing to review or refresh is that there are fundamentally only two different ways to connect multiple resistors in a circuit. The first is known as connecting them in series. When you connect resistors in series, the electrons have to go through all of the resistors before they return to the battery. That first picture is sort of a realistic picture of a circuit with two light bulbs in series, and the second one is a schematic or a circuit diagram showing 4 resistors in series. There is an equation that allows us to calculate the resistance of multiple resistors in series, and it looks a little bit funny, but it basically just says add up the values of all of the individual resistors, and that will tell you the resistance of the series. This should make sense because if you remember what we learned about resistivity, it has to do with the length of the wire or the length of the device that the electrons are going through. When you add resistors in series, you're basically creating a longer resistor each time you add another resistor in series, and so that's going to cause the resistance to go up. The second thing that's true about series circuits is that you must have the same amount of current going through all of the resistors in the series. This goes back to the junction rule. There are no junctions, right? There's no split-off locations for the current. Therefore, we have to conserve mass and keep the current the same everywhere in a series. The voltage, on the other hand, is going to be shared between the resistors that are in series. This is because they're part of a single loop, right? And that means that if there's only one place that energy is going in at the loop, like the battery, then the energy that's being used up at the other spots in the loop, like the resistors, can't use up all the energy of the battery, or the electrons wouldn't return to the same energy state when they return to wherever they started. So the voltage is going to be shared between the resistors in a series because they're all part of the same loop, and there is a linear relationship between voltage and resistance, which means whichever resistors in that loop have the largest resistance will get the biggest share of the voltage. Consequently, they're also going to be the brightest because the same current but more voltage is going to be more power. The second way of connecting two or more resistors in a circuit is called in parallel. When you connect resistors in parallel, electrons have a choice of which path to take back to the battery. There's a sort of drawing of two light bulbs connected in parallel. You'll see that the electrons leave the battery and they can either go through the first light bulb or the second, but not both. And here is sort of a weird looking circuit diagram or schematic showing 3 resistors in parallel. Again, the electrons have a choice of which one of those they want to go through. Just like we did with our series circuit, we can calculate the resistance for resistors in parallel directly with an equation. The equation, shown below, basically means that you add the sum of the reciprocals of the resistors, and then you take the reciprocal of the answer. We'll do some practice on this in class, but the big idea is make sure you put everything on, on the reciprocal or on the denominator of the fraction, and then take that last reciprocal at the end to get your final answer. When you've used this equation, you'll discover that the net result is that every time you add a resistor in series, the resistance of the circuit decreases. If you think again back to our definition of resistance, right? This was a series circuit. A parallel circuit basically has the two resistors side by side. This is allowing more paths or more width for the electrons to go through, and therefore it's a lower resistance. In parallel circuits, you're going to see that the same voltage drop happens on each branch of that parallel circuit. That's because the electrons have to return to the battery having lost the same amount of energy no matter which pathway they take. So if there's 3 resistors in parallel, the voltage will be the same for each one of those because each one is in its own loop. The current, however, does not have to be the same because we have a junction before and after each of those resistors. So the current is going to split, and what you will find is that more current goes to the smaller resistance path in this case, and it follows the mathematical relationship of I is inversely proportional to R. So you can use that to help figure out how much current is going to each of the branches. Okay, I'm going to fly through this slide, but feel free to pause it and solve it yourself if you feel like that would help you understand this more. We have a very basic series circuit, and I'm going to solve this one conceptually, and then we'll look at some more complicated ones with equations. So in this circuit, we know that we have a 12-volt battery, we have a 100 ohm resistor labeled R1, and a 200 ohm resistor labeled R2. One of the tools I like to use is called a VIRP table, although actually the VIRP table will be a little bit slow for the AP test, but we can see the patterns really nicely on this, and ultimately you can kind of jump to the spots that you actually need without doing the entire table. But for now, we label our VIRP on the left, they stand for voltage, current, resistance, and power, and then on the top we label each of the resistors in the circuit as well as a column for sort of the total circuit values. I'm going to put in my known values right away. I know that 100 ohm is R1 and 200 ohms is R2, and I know that the total voltage provided to the circuit, because there's only one battery, is 12 volts. You can, at this point, use your resistance equation because these resistors are all in series, so you can just add up the resistance when we have multiple resistors in series, which tells me my total resistance is going to be 300 ohms. The goal is to fill out the entire table, but what you should know is that anytime you can get 2 known values in a single column, then my Ohm's law and my power equation work to solve the other 2. So once I've got those 2, I can use I equals V over R to solve for the current that's coming out of the battery, and P equals IV to find the power. Then it goes back to thinking about physics. We're in a series circuit. That means that there are no junctions. So if 0.04 amps of current are coming out of the battery, that same current has to travel through the entire circuit and back to the other end of the battery. So we must be able to put 0.04 amps in for the current through R1 and also through R2. Now we've got 2 known values in each of my columns, my other 2 columns, so we can use Ohm's law to find the voltage for each of those, and we can use the power equation to calculate the power. Now that we're done, you should look back at your values and make sure everything makes sense. We found that the voltage drop at R1 was 4 volts, the voltage drop at R2 was 8 volts, and the total voltage provided to the circuit was 12. This should make a lot of sense when you think about the loop law, right? The electrons have to be in the same energy state when they return to wherever they started. So they're going to be gaining 12 volts at the battery, and then dropping 4 of that in the first resistor and 8 in the second, and then we're back to gain our 12 again, and you can see that energy there is going to be conserved. You'll also notice that each electron used a higher percent of its total energy in the harder resistor, so the 200 ohm resistor got twice as much voltage as the 100 ohm resistor did. That ratio is proportional to the resistance, so it ends up being a nice shortcut if you can just say, well, it's a 1-to-2 ratio on resistance, it'll be a 1-to-2 ratio here on voltage. The current makes sense as well. I mentioned this before, there's only one path, so the same number of electrons go through the entire circuit. The resistance of the circuit makes sense. It's going to have a large total amount of resistance because each electron has to pass through multiple resistors. They're sort of, daisy chaining on the length. And the power column should make sense as well because we're going to see that there is more power dissipated at the higher resistant bulb. They both have the same current, but that bulb gets more voltage. I am going to point out that when you make these VIRP tables, a good way to double check that you've done them right is to make sure that the total power is always going to be the sum of the individual powers. So 0.16 plus 0.32 gives you 0.48, so we know that we've probably done this circuit correctly. All right, let's go through a parallel circuit and a VIRP table. We're going to take the same two resistors and the same battery, and we're going to put them in parallel this time. The no list is the same from the beginning, but our first step is going to be a little bit different this time. We can't just add up my resistance. We could use our parallel equation to add up the resistance, which we'll do in a minute here. But another way to get into the rest of the table is to realize that each of those resistors is the only resistor in a loop with the battery, right? There's two loops, one that goes through R1 and a different loop that goes through R2, which means that if the loop law is going to apply and the battery gives 12 volts, we also have to use up 12 volts whether we go through R1 or whether we go through R2. So that allows me to get two known variables in each of those columns, which of course is very useful because I can then calculate the current, which is 0.06 amps and 0.12 amps, and the power as shown. From here, let's take a look and see how we can get into the total column. One way is by using the junction rule at either of those two junctions labeled with the big black dots. Since we know that the current into the junction has to equal the current out of the junction, if we have 0.06 amps going through R1 and 0.12 amps going through R2, the total current coming out of the battery must be 0.18. This, of course, then allows us to calculate the other two variables in this column based on my two equations. Again, when you look at this table, it's going to look totally different than the last table. And so this is where you really did have to understand the physics because the numbers in your no list were the same, but the physics is completely different. The voltage in this table makes sense because in Kirchhoff's loop rule, each of those resistors is in its own loop. The current should make sense. Not only does it add up to the total current because of the junction law, we'll also notice that a higher proportion of the current is going to go through the easier path, which is going to be my R2, my 100 ohm resistor. Just like in the last situation, we can actually use proportional reasoning. Current is inversely proportional to resistance, which means if we have twice as much resistance, we're going to have half as much current. So you'll notice it's like a 1-to-2 ratio on the current as well. So that can help you solve these things really fast. The resistance value for the whole circuit is 67 ohms, and that tends to jump out as weird to a lot of people because the resistors were both bigger than that. But remember, we actually made the resistance smaller by making those resistors basically wider by connecting them in parallel. So if you don't end up with a total resistance that's smaller than either of the individuals, you've done it wrong. The power makes sense as well because in this case we're going to have more power dissipated by our lower resistance bulb. They have the same voltage, but that bulb gets more current. And you'll see that the power values add up again at the bottom. I wanted to go back and just show you that you can double check, or you could lead even in with the calculation of your total resistance using your parallel resistance equation. What that looks like here is 1 over the total resistance is equal to 1 over 100 plus 1 over 200. When you add those together, you get 1 over R equals 3 over 200. Okay, and then don't forget to take that very last step, which is the reciprocal of both sides. That gives you the direct answer, which is RS67, which confirms what we got from our other method. A complex circuit is a circuit that has series and parallel portions sort of nested within each other. So you can take a look and see at that circuit drawn below. We have three things in parallel, but then we have a little, three things in series, then we have a little parallel nested inside. The loop and junction rule that we learned earlier are going to apply through each chunk of a circuit that fits one of the two patterns we learned about. Wherever we have resistors in series, we're going to make sure that the current is the same through any of those resistors that are in series. We also can use the junction rule at the two junctions shown in this circuit. So we've learned that earlier, and that rule is going to work and apply at those two junctions. Those are my three resistors in series, and they're going to have the same current. And in fact, it's going to be the same as the total battery current because they're also in series with the battery. The loop law applies when we talk about voltage in this circuit. The voltage is going to be the same in any portions of the circuit that are parallel with each other. So for example, the voltage drop must be the same across those two resistors. But you can also use the loop rule for any of the loops in this circuit. There's actually three loops in the circuit. There's two big ones that include the battery, and there's a little tiny loop that just includes the 12 and the 6 ohm resistor. Any case, the same rules apply for any of those three loops. One important skill to develop is redrawing circuits. When you get a really complicated circuit, what we usually do is sort of like simplify it by steps. We start at the tiniest portion that is purely series or purely parallel, and we use our equations to figure out what single resistor could we replace the series or parallel portion with that would have the same equivalent value. So I'll show an example of this. We have a complicated circuit on the left, one of those complex circuits. I'm going to redraw this twice. In the first redrawing, I'm going to replace the parallel portion of that circuit. We had a 12 ohm and a 6 ohm resistor in parallel. If you use your equation, 1 over 12 plus 1 over 6 equals 1 over 4, and then you take the reciprocal. So we could imagine pulling out those two single resistors and replacing them with one resistor that is a 4 ohm resistor. Now we have a circuit that's all series. So that's really nice because we can use a single another equation to figure out what is the equivalent resistance of the whole circuit. We just add them all together, and you end up discovering that the resistance of the circuit is 19 ohms. This is useful from a variety of perspectives. It can be really useful to very quickly figure out what's the total current in the circuit, because if you know the total resistance and the battery voltage, that'll tell you the total current and the total power in the circuit. But it also can be used to find information about individual chunks or individual resistors in the circuit, because it turns out that Ohm's law, the power equation, and the junction rule and the loop rule all apply both conceptually and mathematically in every portion of every redrawing, right? So I could zoom in on the individual resistors in my very first drawing and all those equations and relationships apply. Or I could look at diagram C and maybe zoom in on just that 4 ohm portion that I kind of created, and those equations are going to apply as well. If you find yourself in a situation where you're asked to solve a complex circuit either computationally or algebraically, you're going to want to start by labeling all the things you can possibly label. Label all your resistors and your batteries with current, voltage, and resistance values. You will notice that I did a couple things here. When I was labeling my current, I drew arrows to represent the expected direction of that current. I'm going to call that the positive direction, and I'm going to make it positive in my equations. Occasionally, when you're done with all your math, you discover a negative value for one of your currents. And what that means is you made a bad guess on the direction of the current. This happens with more complicated circuits where it might be harder to predict. So in any case, draw an arrow that is your prediction of what direction the currents are. In terms of the voltage, you'll notice I labeled my voltage at the resistors as negative values. The standard is to add voltage at a battery and lose voltage at a resistor, so it helps me to kind of picture it in positive and negative terms. It's also very useful when we have a circuit like this to find REQ of the circuit using the combination of the resistance equations and some algebra. So you should be able to find REQ algebraically even without numbers, right? So if we know, you know, that R1 and R2 and R3 are all equivalent to each other, you should be able to use a combination of your resistance equations to calculate the equivalent resistance in terms of R. And we'll do some practice with that in the class, but I've seen a lot more of that popping up recently. After that, then the next thing that you're sometimes asked to do, or is another important step along the way to solving the circuit, is to come up with sort of a formal application of Kirchhoff's junction rule, or write an equation that represents Kirchhoff's junction rule. Of course, that rule says that the current flowing into a junction must equal the current flowing out of a junction because of conservation of mass. So there's two junctions in this circuit. You can write an equation for each one. On that top junction, we know that I1 must equal I2 plus I3 because the way we've drawn current, I1 is going in and I2 and I3 are coming out. And then, of course, we could write an equation for the other junction as well that would say I2 and I3 are coming in and I1 is going out. Those equations are the same as each other, but sometimes you might have more complicated series of junctions. You can also write equations using Kirchhoff's loop rule. Remember that the potential difference around any closed loop is always zero due to conservation of energy. We're going to consider voltage going through a battery, at least in the correct direction, to be positive and negative at the resistors. So I am drawing three possible loops you can write equations for in this particular drawing. In that first loop, we're going to write an equation that says VB, which is a positive value because we pass through the battery in the positive current direction, minus V1 because we lose voltage at R1, minus V2, this is the yellow loop, equals 0. So that's our first equation according to the loop rule. Second equation is going to be for the green loop. V battery is positive, minus V1, minus V3, and then we're back to 0. And then the last equation is for the purple loop. This one's a little bit funky because one of the directions of the loop is going opposite from the direction that I made my current standard. So in this problem, I made V2 positive because we're actually going upstream through V2, right? That should be towards the battery or increasing in voltage. So V2 minus V3 is that third equation. Once you've gotten all of your sort of possible equations, you can create and evaluate a system of equations that can allow you to mathematically find any value that you're interested in. So for example, these are some of the equations that we had. We had I1 equals I2 plus I3, and VB minus V1 minus V2 is 0, and V2 minus V3 is equal to 0 as well. We're trying to reduce the number of variables in this system because what we ultimately want to get to is as many equations as we have unknown. So in this case, we have a whole bunch more unknowns than we have equations. But one way to help us get simplified is by using Ohm's law to replace the V values with I times R. So you'll notice in that second series of equations, I've replaced V1 and V2 with I1R1 and I2R2 and etc. So this lets me get my equation just in terms of currents and resistances in that one battery voltage. And you know, at this point, like, you're either solving algebraically or they've given you enough values to plug in that there's only a couple unknown variables, and you can isolate those variables, replace them into other equations like we've done when we derive an equation, and ultimately boils down to a single value for each variable. This tends to be longer than they are wanting you to spend on the AP test, but what they will do is ask you to evaluate whether the equation matches the picture, right? So they might give you these equations and say, are those true equations for this scenario or this setup? And you'd need to know that they either do match or don't match the Kirchhoff's laws that they came from. All right, we made it through the video. Would you please take a few minutes to review the essential question, which is how do you organize your data, use equations and conceptual modeling to predict the behavior of complicated circuits? Thanks for watching.